Hello. So far we have discussed what a power series is, and we have also defined what is the radius of convergence and the interval of convergence of a power series. Now our goal is to learn to find the power series associated to a function at a point. We have worked with the following series. I'm going to be summing from 0, and it's centered at 0, so we have x to the power of n divided by n factorial. We have worked with this series. We have seen that it has infinite radius of convergence. So for each value of x in the real numbers, the series is a convergent numerical series. And I have said that this is the power series associated to the function e to the power of x. This is something that we have not formally justified. But what we want to see now is, well, if we have a function, a transcendental function, for instance, like e to the power of x, how can we find the associated power series, for instance, centered at 0? And this is what we're going to learn now. Given a function, let's say f of x, we are going to find a polynomial that approximates the function. So we're going to associate a polynomial of degree n. And that's what we are going to call the Maclaurin or the Taylor polynomial associated to this function. Then later on, we are going to let n be infinite. So we're going to be looking at, quote, infinite polynomials. And that's going to be the Maclaurin or Taylor series associated to the function. So how do we do this? We have our function f of x, and we're also going to fix a point c. And we're going to find the Taylor polynomials centered at c for the given function. We are going to begin by considering a polynomial of degree 0. Well, a polynomial of degree 0 is just a constant. So we want a constant that in some sense approximates the function f of x when x is equal to c. So actually what we're going to consider is just the value of the function at c. So our function and the constant function coincide at the point c. So this is going to be p0 of x. So this is the polynomial of degree 0 that we are trying to define. Now we want to look at a polynomial of degree 1. So this is going to be a linear function. So we are going to require two things. We want, let's say we call it P1. We want this P1 to coincide at c with the value of the function at c. But we also had the condition that we want the derivative to coincide with the derivative of the function at c. So now we have two conditions for the linear polynomial we are trying to find. But this is exactly what the tangent line does. If we want to write the line tangent to the function f at the point c, we'll write that y minus f at c has to be the same as f prime at c times x minus c. This will be the point slope form of the tangent line. But, well, if we write our polynomial of degree 1 as a function of x is the function at c plus the derivative of the function at c multiplied by x minus c. This polynomial satisfies the two properties that we want. If we evaluate at c, the result is f of c, and if we evaluate the derivative at c, the result is the derivative of the function at c. So this is the polynomial we are looking for, and it's actually the formula for the tangent line at the point. For degree 2, now we are going to be talking about a quadratic. We are going to require still that our polynomial, I'm going to call it P2, evaluated at C takes the same value as the function. The derivative of the polynomial evaluated at C takes the same value as the derivative of the function. And the second derivative evaluated at C takes the same value as the second derivative of the function evaluated at C. Well, this polynomial is going to be given by, we are going to start exactly like the polynomial we had before, because that's a polynomial of degree 1 that verifies the property that we want. Sorry, correct here. So we start with the value of the function evaluated at C plus the value of the derivative evaluated at C times x minus C. And now we need to add what is going to give us the second degree polynomial. So there is going to be x minus C to the power of 2. And the question is, what is the coefficient that we need to write here? Let me call it A2. Well, let's check. Let's take the first derivative of this polynomial. Well, that's going to be f prime at C plus 2 times whatever that constant that I call A2 is, times x minus C. And if I take the second derivative, I'm going to have, well, this disappears, so I'm going to have 2A2. And what we know is that we want this 2 times A2 to be the second derivative of the function evaluated at C. So we can find that we want the value of A2 to be the second derivative of the function evaluated at C divided by 2. So the novelty with respect to the pattern that we had before is that now we have this divided to what we didn't have. So let's write what our polynomial is. P2 of x is function evaluated at C plus the derivative of the function evaluated at C times x minus C plus second derivative of the function evaluated at C divided 2 times x minus C squared. Could be convenient to simplify a bit the notation, to call this first value of the constant polynomial of degree 0 A0, so the value of the function at C, and we could also call the value of the function, the derivative of the function at C A1, and well, we found the value of A2 over here, so we could also use those coefficients to write down what we have so far. So we are saying so far P2 of x is A0 plus A1 x minus C plus A2 x minus C squared. Let's find the next polynomial. Now we are talking about a cubic polynomial, 3 cubic, and well, guess the conditions we have. I'm going to call it P3 at C has to take the same value of the function. Its first derivative has to be its first derivative of the function, and so on. So maybe we can just write this in a shorter form, writing this between brackets, and that means the nth derivative if n is greater or equal than 1, or otherwise just the function itself. So we have now a list of 4 conditions we want to be verified by our polynomial. Our polynomial, in order to verify those 4 conditions, is going to be actually the previous polynomial we found, so P2 of x plus a new term that is going to have some constant A3 multiplied by x minus C to the power of 3. And well, we want to find what is this value A3 that we are missing, and you may have a guess of what it should be. I encourage you to write down your guess and let's check if you're correct or not. When we consider the first derivative of the third polynomial, we will be taking the first derivative of the second polynomial, so f prime at C plus 2 times A2 x minus C plus 3 times A3 x minus c squared. That was for the first derivative. Let's go ahead and take the derivative one more time. So now the constant is gone, so we're going to have 2 times a2 plus 3 times 2. Yeah, this z2 is coming from taking the derivative of the binomial x minus e to the power of 2 times a3 times x minus c. And let's take the third derivative. Now is the interesting one. The constant is gone, so we are going to have 3 times 2 times a3. And we want this value to be the value of the third derivative of the function evaluated at c, which means that we can find that the value of the constant a3 we were missing is the third derivative of the function at c divided this time by 3 times 2, but notice this is 3 factorial. And now maybe you are seeing the pattern. We could keep going like this for a while, but I'm just going to write what the pattern is. So what will be the polynomial of degree n? I want to write a very important note over here. Over here, for all of this to make sense, we need to assume that we can take the derivatives of our function at least n times. So assume derivatives of f exist at least up to the nth derivative. Yeah, because we are working with that, so we have to make sure that this is actually well, possible for us to do. Well, if we can't do it, then our polynomial of degree n, that I'm going to call it Pn of x, this polynomial, it's the Taylor polynomial of degree n of f at x equals c. So we have the degree, we have the function, and we also have the point around where we are calculating this polynomial. But we are going to have the sum from m equals 0 to n. We are going to have some coefficients, am, we are going to say what they are, and then we are going to have x minus c to the power of m. And what do we want m to be? Well, if you remember, a0 was just the function at c, a1 was the derivative of the function at c, a2 was the second derivative of the function at c divided by 2, and a3 was the third derivative of the function evaluated at c divided by 3 factorial. But actually here when we wrote 2, we could have written 2 factorial, that wouldn't change the result. And when we wrote a1 is equal to first derivative at c, we could have written it also divided by 1 factorial, and this could be also divided by 0 factorial. So, in other words, what do we want for the m coefficient of the polynomial we are trying to find? Well, we want it to be the m derivative of the function evaluated at c divided by m factorial. So, this is what we wanted to define. This is how we find the Taylor polynomial associated to a function at a point of degree n. If, well, we need to have the derivatives to make sure we can do this. If c is equal to 0, then we have a particular case. It just looks a little bit easier because we have x to the power of m, and for the coefficients we just evaluate them at 0. And this is what we call the Maclaurin polynomial. Maclaurin polynomial, again, degree n for f at 0.